My name is Daniel Ansari. I'm an assistant professor in the Department of Psychology at Western and the Canada Research Chair in Developmental Cognitive Neuroscience. Dyscalculia is a specific learning difficulty in the domain of mathematics. It's when you struggle with math in everyday situations, such as calculating a tip when you're in a restaurant or knowing how much change you should expect to get back from a cashier. Very few people know what it is, and yet it's just as common as dyslexia, and can have a significant impact for people who are affected by it. While there was a lot of information about how the adult brain processes numbers, little was known about how children solve mathematical problems and what sort of brain mechanisms are involved with that. My research really started to explore, perhaps for the first time, how it unfolds over developmental time and how we can eventually help children who are affected by this disorder. The study that we're currently conducting is looking at what brain areas are involved when you calculate. Another thing is to understand how brain function and brain structure interact with one another as we learn, as we develop, because often we address them very separately, and there's now a growing trend with these new imaging technologies to be able to combine what we know about brain structure with what we know about brain function. I was attracted to Western because of its research excellence, its positive environment for researchers, and also particular to the neuroimaging facilities at the Robarts Research Institute. This type of equipment is absolutely critical to my research. It's finding stuff out, it's making discoveries, it's answering questions. The ultimate goal of my research is to better understand what causes developmental dyscalculia, how it unfolds over developmental time, and how we can eventually help children who are affected by this disorder.
These are the famous dots, so you just have to say how many dots there are. Two, that's very good. And you're quite quick. Now the next one.
6.
Okay, you're accurate there, but you're a bit slower. Well, I've been particularly interested in the last few years in dyscalculia, which is a congenital condition that affects somewhere between 3 and 6% of the population. And what it means is that they're very, very bad at learning arithmetic, at least learning it in the normal way. And this seems to be a lifelong condition. We've met a lot of adults who have this condition. Adults who are very successful in other branches of other walks of life that don't depend very much on being good with numbers. I mean, they can be filmmakers, TV producers, they can even be science journalists, though they're not going to be terribly good at doing the maths for physics. Well, it's like dyslexia in the following way, that it's something that you're meant to learn at school, and that unless you have special help, you're not going to learn it at school. It's not exactly the same as dyslexia, though it's often called dyslexia for numbers, because dyslexia is a problem in reading, but in fact it's really a problem of language, dyslexia. So you have a particular problem with analysing the sounds of language, and that's really what prevents you from linking letters with sounds, particularly for an orthography like English orthography, where the relationship between letters and sounds is not particularly consistent.
What's the difference between someone who has dyscalculia and someone who's just a bit rubbish at math?
The difference between dyscalculia and just being rubbish at maths is that lots of reasons for being rubbish at maths. My own excuse is that I didn't have a very good maths teacher at school, and I didn't like him, I didn't get on with him. I've had to try and desperately to make up for that since. For example, you might miss a lot of lessons, and since maths is a kind of cumulative subject, unlike history, then you know, if you miss a lot of stuff, it's very hard to catch up. Dyscalculia can occur in people with high intelligence, good memories, who go to school every day, have you know, really supportive backgrounds, and yet they're unable to do what everybody else in their class can do. They do simple arithmetic. So there is a difference. You can often spot a dyscalculic, though these aren't formal tests, in lots of different ways. For example, they have great difficulty in remembering telephone numbers. They have difficulty in remembering any numbers. So they often are going to use the same PIN when they shouldn't, for lots of different activities. They're very bad at shopping. So actually one of the first developmental dyscalculics that we came across was in prison, and he was in prison for shoplifting. Why did he shoplift? Well, because he was too embarrassed to go to the counter, because he didn't know how much money to give, he didn't know whether he was getting the right change. So shopping is an area which is really difficult for dyscalculics. They also have trouble with time. It's not that they can't estimate intervals, it's just that they're not very good at the numerical side of it, working out, for example, what time they have to leave home in order to get to somewhere at a particular time. We know that there's a particular part of the brain that seems to be involved in very simple number tasks. So, for example, here in the parietal lobes of the brain, this is the back of the brain, this is the left parietal, that's the right parietal. We know that these areas are critical for just enumerating the number of objects in a set. One of the things that we know is that, we now know, and it's a very recent discovery, is that dyscalculics have abnormalities, particularly in both of these areas, and maybe particularly in the left in older dyscalculics. So they have abnormal structure, and also the brain activates in a different way when they're doing number tasks. Now, why should they have abnormal structure or abnormal activations? Well, there are a number of possible reasons. We don't know all of them. One of them is these abnormalities seem to be, in some cases, inherited. One of the things we do know is that there are particular genetic abnormalities that seem to affect numbers more than other cognitive abilities. So abnormalities in the X chromosome seem to have an effect on parietal lobe development and also on numerical abilities. So individuals with a number of different X chromosome conditions like Turner's syndrome, where you have only one complete X chromosome, or Fragile X syndrome, they seem to have a big effect on your ability to do even very simple number tasks. In the study that we've just published, we used two criteria. One is you've got to be bad at arithmetic, and it's important to note it's timed arithmetic that's critical here, because there's a difference between somebody who answers the question, what's 5 plus 3 with 8, and the individual who goes 5 plus 3, 8. So time is a very good diagnostic here. And we also looked at the ability to just enumerate sets. So how many dots are there on the screen? Now, how good you are at this is even in kindergarten, in one of our studies, is a very good predictor at how much difficulty you're going to have in learning arithmetic.
What is it about counting dots? Counting dots is it just because it's a good, easy, dependable test, or is there something more to it that I'm missing?
It's a very dependable test. So if you're bad at it at 5, you're bad at it at 6, you're bad at it at 7, you're bad at it, well, up until 11, that's, in our longitudinal study, that's as far as we've gone so far. So it's a very stable indicator. So that's one reason. The other reason is because it links to the kinds of things that might be inherited, the kinds of things that other species are able to do.
What do we do with someone who's got it then? Are there drugs they can take? Is there something that can be done, or are they a basket case?
No, they're not basket cases, but like dyslexia, what you need is special kinds of intervention. So if they're not very good at enumerating sets, it means they don't have a very good sense of the number of objects in the set. So if it's a set of 5, not very good at enumerating it, means they don't have a very good sense of what 5ness is. So what you have to do is you have to have interventions that target that particular weakness. So you get lots of practice at enumerating sets, linking that enumeration with the symbols that we use for sets, like the word 5 and the digit 5. And in fact, you can relate the number of dots to how long it takes you. So unsurprisingly, you might say the more dots there are, the longer it takes you to give the right answer. But there's a very reliable result, which we've known for at least 50 years, which is that up to about 4 dots, you're very accurate and you're pretty fast. And thereafter, it takes you about an extra quarter of a second for each additional dot. And this is sometimes called the subitizing range, and that's called the counting or estimating range. And there's a point at which you go from one range to the other range, and that suggests there are actually two processes at work here. And we know actually from some recent neuroimaging studies that we've done that there are in fact, there's a separate part of the brain that does the subitizing range from the estimating range.
Can I ask you to please recall a time when you really loved something, a movie, an album, a song, or a book, and you recommended it wholeheartedly to someone you also really liked. And you anticipated that reaction, you waited for it, and it came back, and the person hated it. So by way of introduction, that is the exact same state in which I spend every working day of the last 6 years. I teach high school math. I sell a product to a market that doesn't want it, but is forced by law to buy it. I mean, that's kind of, it's just a losing proposition. So there's a useful stereotype about students that I see, a useful stereotype about you all. I could give you guys Algebra 2 final exam, and I'd expect no higher than a 25% pass rate. And both of these facts say less about you or my students than they do about what we call math education in the US today. To start with, I'd like to break math down into two categories. One is computation. This is the stuff you've forgotten. For example, factoring quadratics with leading coefficient greater than 1. Okay? This stuff is also really easy to relearn, provided that you have a really strong grounding in reasoning, math reasoning. We'll call it the application of math processes to the world around us. This is hard to teach. This is what we would love students to retain, even if they don't go into mathematical fields. This is also something that, the way we teach it in the US, all but ensures they won't retain it. So I'd like to talk about why that is, why that's such a calamity for society, what we can do about it, and to close with why this is an amazing time to be a math teacher. Okay? So first, five symptoms that you're doing math reasoning wrong in your classroom. Okay? One is a lack of initiative. Your students don't self-start. You finish your lecture block, and immediately you have 5 hands going up, asking you to re-explain the entire thing at their desks. Students lack perseverance. They lack retention. You find yourself re-explaining concepts 3 months later, wholesale. There's an aversion to word problems, which describes 99% of my students, and then the other 1% are eagerly looking for the formula to apply in that situation. Okay? This is really destructive. David Milch, a creator of Deadwood and other amazing TV shows, has a really good description for this. He swore off creating contemporary drama, shows set in the present day, because he saw that when people fill their mind with 4 hours a day of, for example, 2.5 Men, no disrespect, it shapes the neural pathways, he said, in such a way that they expect simple problems. He called it an impatience with irresolution. You're impatient with things that don't resolve quickly. You expect sitcom-sized problems that wrap up in 22 minutes, 3 commercial breaks, and a laugh track. And I'll put it to all of you, what you already know, that no problem we're solving is that simple. I'm very concerned about this because I'm going to retire in a world that my students will run. I'm doing bad things to my own future and well-being when I teach this way. I'm here to tell you that the way our textbooks, particularly math-adopted textbooks, teach math reasoning and patient problem solving, it's functionally equivalent to turning on 2.5 Men and calling it a day. In all seriousness, here's an example from a physics textbook. It applies equally to math. Notice, first of all, here that you have exactly 3 pieces of information there, each of which will figure into a formula somewhere eventually, which the student will then compute. Okay? I believe in real life. And ask yourselves, what problem have you solved ever that was worth solving where you knew all of the given information in advance, where you didn't have a surplus of information and you had to filter it out, or you didn't have insufficient information and had to go find some? I'm sure we all agree that no problem we're solving is like that. And the textbook, I think, knows how it's hamstringing students, because watch this. This is the practice problem set. When it comes time to the actual problem set, you have problems like this right here, where we're just swapping out numbers and tweaking the context a little bit. And if the student still doesn't recognize the stamp this is molded from, it helpfully explains to you like what sample problem you can return to find the formula. Like you could literally, I mean this, pass this particular unit without knowing any physics, just knowing how to decode a textbook. That's a shame. So I can diagnose the problem a little more specifically in math. Here's a really cool problem. I like this. It's about defining steepness and slope using a ski lift. But what you have here is actually 4 separate layers. And I'm curious which of you can see the 4 separate layers, and particularly how when they're compressed together and presented to the student all at once, how that creates this impatient problem solving. I'll define them here. You have the visual, okay? You also have the mathematical structure, talking about grids, measurements, labels, points, axes, that sort of thing. You have sub-steps, which all lead to what we really want to talk about, which section is the steepest. So I hope you can see, I really hope you can see how what we're doing here is taking a compelling question, a compelling answer, but we're paving a smooth, straight path from one to the other and congratulating our students for how well they can step over the small cracks in the way. That's all we're doing here. So I want to put to you that if we can separate these in a different way and build them up with students, we can have everything we're looking for in terms of patient problem solving. So right here, I start with the visual, and I immediately ask the question, which section is the steepest? And this starts conversation because the visual is created in such a way where you can defend 2 answers. So we get people arguing against each other, friend versus friend, in pairs, journaling, whatever. And then eventually we realize it's getting annoying to talk about the skier in the lower left-hand side of the screen, or the skier just above the midline. And we realize how great would it be if we just had some A, B, C, and D labels to talk about them more easily. And then as we start to define like what does steepness mean, we realize it'd be nice to have some measurements to really narrow it down specifically what that means. And then and only then we throw down that mathematical structure. The math serves the conversation doesn't serve the math. And at that point, I'll put it to you that 9 out of 10 classes are good to go on the whole slope steepness thing. But if you need to, your students can then develop those sub-steps together. Do you guys see how this right here compared to that, which one creates that patient problem solving, that math reasoning? It's been obvious in my practice to me. And I'll yield the floor here for a second to Einstein, who I believe has paid his dues. He talked about the formulation of a problem being so incredibly important. And yet, in my practice, in the US here, we just give problems to students. We don't involve them in the formulation of the problem. So 90% of what I do with my 5 hours of prep time per week is to take fairly compelling elements of problems like this from my textbook and rebuild them in a way that supports math reasoning and patient problem solving. And here's how it works. I like this question. It's about a water tank. The question is, how long will it take you to fill it up, okay? First things first, we eliminate all the sub-steps. Students have to develop those. They have to formulate those. And then notice that all the information written on there is stuff you'll need. None of it's a distractor, so we lose that. Students need to decide, all right, well, does the height matter? Does the side length matter? Does the color of the valve matter? What matters here? It's such an underrepresented question in math curriculum. So now we have a water tank. How long will it take you to fill it up? And that's it. And because this is the 21st century, and we would love to talk about the real world on its own terms, not in terms of line art or clip art that you so often see in textbooks, we go out and we take a picture of it. So now we have the real deal. How long will it take it to fill it up? And then even better is we take a video of someone filling it up. And it's filling up slowly, agonizingly slowly. It's tedious. Students are looking at their watches, rolling their eyes, and they're all wondering at some point or another, man, how long is it going to take to fill up? That's how you know you've baited the hook, right? And that question off this right here is really fun for me because like the intro, I teach kids, because of my inexperience, I teach the kids that are the most remedial, all right? And I got kids who will not join a conversation about math because there's, like, someone else has the formula. Someone else knows how to work the formula better than me, so I won't talk about it. But here, every student is on the level playing field of intuition. Like, everyone's filled something up with water before. So I get kids answering the question, how long will it take? I got kids who are mathematically and conversationally intimidated joining the conversation. We put names on the board, attach them to guesses, and kids have bought in here. And then we follow the process I've described. And the best part here, or one of the better parts, is that we don't get our answer from the answer key in the back of the teacher's edition. We instead just watch the end of the movie. And that's terrifying, all right? Because the theoretical models that always work out in the answer key, the back of the teacher's edition, like that's great, but it's scary to talk about sources of error when the theoretical does not match up with the practical. But those conversations have been so valuable, among the most valuable. So I'm here to report some really fun games with students who come pre-installed with these viruses day one of the class, okay? These are kids who now, one semester in, I can put something on the board totally new, totally foreign, and they'll have a conversation about it for 3 or 4 minutes more than they would have at the start of the year, which is just so fun. We're no longer averse to word problems because we've redefined what a word problem is. We're no longer intimidated by math because we're slowly redefining what math is. This has been a lot of fun. I encourage math teachers I talk to use multimedia because it brings the real world into your classroom in high resolution and full color. To encourage student intuition for that level playing field, to ask the shortest question you possibly can and let those more specific questions come out in conversation. To let students build the problem, because Einstein said so. And to finally, in total, just be less helpful. Because the textbook is helping you in all the wrong ways. It's helping you, it's buying you out of your obligation for patient problem solving and math reasoning to be less helpful. And why this is an amazing time to be a math teacher right now is because we have the tools to create this high quality curriculum in our front pocket. It's ubiquitous and fairly cheap. And the tools to distribute it freely under open licenses has also never been cheaper or more ubiquitous. I put a video series on my blog not so long ago, and it got 6,000 views in 2 weeks. I get emails still from teachers in countries I've never visited saying, wow, yeah, we had a good conversation about that. Oh, and by the way, here's how I made your stuff better. Which, wow. I put this problem on my blog recently. You're in a grocery store, which line do you get into? The one that has 1 cart and 19 items, or the line with 4 carts and 3, 5, 2, and 1 items? And linear modeling involved in that was some good stuff in my classroom, but it eventually got me on Good Morning America a few weeks later, which is just bizarre, right? And from all of this, I can only conclude that people, not just students, are really hungry for this. Math makes sense of the world. Math is the vocabulary for your own intuition. So I just really encourage you, whatever your stake is in education, whether you're a student, parent, teacher, policymaker, whatever, just insist on better math curriculum. We need more patient problem solvers. Thank you.